In this video, a resistance temperature detector circuit is explained using a PT100 RTD temperature sensor with error compensation for nonlinearity that is discussed and analyzed. This is the 215th video in the circuit analysis playlist. Circuit is implemented with one op-amp that is a low noise, low input voltage offset, the likes of that you can find from Texas Instruments or analog devices in DigiKey or Mauser. At the input, we have a PT100 RTD or resistor that is depending on temperature, which is usually a platinum-based device. So PT100 is a well-known one with this sort of a relationship between the resistor RT and temperature in degree C. The input temperature measured in this example is between 0 to 400 degrees C, but these things can go below 0 and can go above 400 to 900. The kind of an output voltage that we like to see in this circuit realize is a linear relationship. So as input changing from 0 to 400, we want the output to change from 0 to 8 volt. And in a linear fashion. So what is the slope? Delta V out divided by delta T in is just 8 volt over 400, which is 1 over 50. So the slope is simply 1 over 50. That's the desired behavior. The resulting formula is this one. I'm going to refer to it as formula number 1. Now, let's go back to the RTD. So we would love to have basically beta 0, but unfortunately beta is not 0 and there is dependency on second order nonlinearity, which is the square of the temperature. Alpha and beta are properties of PT100 or positive temperature coefficient 100 ohm default resistor. So in this case, if temperature is 0, we get 100 and we're going to name it as R0. If it is not 0, then we have to follow this formula above 0. Alpha is just 3.91 times 10 to the power minus 3, property of PT100. Beta is unfortunately not 0. It is 5.85. It's 5.78, and then times 10 to the power minus 7. And because of this non-zero beta and dependency on second order nonlinearity, we are suffering from this result. So result is like this. For the RTD resistor temperature characteristic actual versus ideal, we get actual, a bent sort of a curved plot bending downward, versus ideal, linear straight line, the black dotted or dashed line. So for example, at 0 degrees C at input of the RTD, we have 100 ohm measured, which means the RT or R0 is simply 100 ohm. Now, at 400 degrees C measured by RTD, what we linearly ideally expect is 262 ohm, but we are seeing 247. So unfortunately, that means there is an error here. So here is one line, and here is another line. So the delta between them roughly is 15, 16 ohm. And things get worse for higher temperature. So we get to a situation that even we're talking about expecting 425 in a linear fashion, but then we are getting 375. So the error is on the order of 50 ohm error that need to be compensated. So that's the meaning of a scenario that we are saying error compensation for nonlinearity is considered in this analog design. So for this case, well, how is it achieved? Well, the best way it is done is via a weak positive feedback that tries to push or sort of bend upward this nonlinear behavior. So by moving this red curve upward so that it becomes as close as possible to the ideal black dash line. That's the plan. How is it achieved? When the temperature is going up, V out goes up. When the V out goes up, via this very large resistor, it provides a weak positive feedback current to increase the voltage of the resistor. And that would basically takes care of exactly this idea of pushing up the curve that is less bent then. But we are careful planning, RP will be large enough on the order of 100 kilo ohms so that compared to RF, which is the negative feedback resistor, the impact of positive feedback is weaker, and therefore the circuit will be dominated by the negative feedback, which is via this route, and therefore will remain stable. The combination of RF, R2, RF, R2, 1K, and mainly RF and 1K will control the gain for a negative feedback and therefore keep the circuit stable. Because the circuit is stable, we also apply 10-volt supply and ground for the two supplies of the op-amp. Op-amp is enforced by dominant negative feedback to stable region, and therefore virtual short is valid for the op-amp, which state that the positive and negative input terminal of op-amp should have the same voltage, which is voltage across the RTD resistor VR, and that would be VR here, and therefore that would be VR here, which means we have VR here. Okay, what about, so that is what is referred to as basically virtual short. So virtual short for the op-amp is valid because op-amp is dominated and controlled by negative feedback. Okay, now the next move is also talking about the bias of the circuit via a 10-volt supply voltage, via 100 ohm. We are providing a minimum of, even if the supply changes by plus minus 1 volt, we are providing a minimum of 8 milliamp bias current to these combination of Zener diodes. Note that these Zener diodes, 3.9, 4.3 volt, add them together, we end up with 8.2 volt DC voltage fixed at the input of the circuit for the supply. Reason for that is that this combination is very powerful in the sense of guaranteeing a very stable 8.2 volt that is not even changing as a function of temperature, practically speaking. Reason for that is this view. So look at this two Zener diodes from Vishay, one in 50 to 28, one in 50 to 29, 3.9 volt, 4.3 volt. And look at their temperature coefficient, which is percentage change in the voltage as a function of delta change in temperature. So one of them, you're talking about negative 0.06% change per degree temperature of junction, and the other one is 0.055% change in voltage as a function of junction temperature change. So they are counteracting each other. So if you have them in series like this, what happens is the 3.9 effectively is 3.9. So the 3.9 effectively is just 3.9 times 1. So let me just make sure I have the right thing. So 3.9 times 1 minus 0.06 divided by 100 times delta T. The other one, 4.3, is 4.3 times 1 plus 0.055 times divided by 100 times delta T. So since these two resistors, these two reverse bias voltages of the Zener diode are almost the same, and since their temperature coefficients almost the same except with a sort of counteracting sign, therefore temperature-wise these two Zener diode, they counteract each other, and therefore the overall 8.2 voltage will become very stable with near zero, practically speaking, temperature coefficient. So that's the reason. Now, let's analyze the circuit. What is the meaning of analysis for this circuit? It means to achieve this sort of output behavior, question is, what is the value of this RF? What is the value of this R2? What is the value of this RP? How can we find them? So we're going to do a quick analysis to show how they are computed. Okay, so let's keep them in place. We have this one, we have this one, and we have the value of R2 unknown. Okay, to compute that, let me just remove this to here, and then we go ahead with the analysis. Okay, quick analysis. So for quick analysis, we need to rely on computing the value of voltage across the RTD, which is VR. So I'm going to use superposition. And for superposition, I'm going to think of contributing 8.2 to voltage here, and I'm going to consider contribution of V out to a voltage here. So there are two forces. So VRTD, or basically just VR, the voltage across the RTD, is equal to effectively voltage divider. So let's just focus on 8.2 as if V out is not there. That's the meaning of superposition. So in that case, we have RTD in parallel with RP, and then as a result, the voltage division between R1 and that parallel. So we're going to have RT parallel with RP divide by RT. So divide by RT parallel with RP and then plus R1 and times 8.2 volt. Okay, for the other one we have effectively same scenario. V out is contributing and we are going to forget about contribution from 8.2 and therefore effectively as if 8.2 is not there and is grounded. So if that is the case, then we end up with RT parallel with R1 then series with RP. So it's a voltage divide. So it would be RT parallel with R1 divided by RT parallel with R1 plus RP and then times V out. Okay, so a couple of assumptions, reasonable assumption. RP, this potentiometer at the positive feedback, will be very large resistor so that we keep positive feedback very minimal. So that will be very much larger than RT. Remember, RT is a 100 ohm resistor that only goes up to, say, as I showed you, to say just 300 or 350 ohm. So it's very small compared to RP. Same thing about R1 default 10K. So R1 will be much, much larger, reasonably practically speaking, compared to RT. With these two in mind, I can simplify the equation. So basically VR now approximately becomes, this thing becomes effectively RT over R1 times 8.2 volt. And the other one, this thing here, effectively becomes RT over RP times V out. And remember, V out from equation 1, so V out from equation 1 is simply 1 over 50 times temperature. So that's equation 1 we had. And let's also name this RT as equation 2 here, the equation for the resistor of the RTD resistor or temperature sensor. So with that said, I can substitute V out using what we have here. Okay, so I can say VR is roughly, and I can factor out RT over R1, and I can factor out 8.2 volt. So I end up with 1 plus then R1 over RP, and then I have 1 over 8.2, then I have 1 over 50, and then I have temperature. So instead of 50 and 8.2, let me just write it as 1 over 410. Okay, so what do we have? This one is referred to as, let's name this guy here. Let's name this coefficient here as gamma. Okay, if we name it that way, then I can effectively write VR is approximately RT over R1. And I'm going to substitute RT later with equation 2, but that's coming later. RT over R1, 8.2 volt times 1 plus gamma times temperature. Okay, so remember, RT is also changing by temperature, so it's not just a linear relationship here. Okay, so be careful about that. Now, let's name this equation 3. Good. What else do we need to do? I'm going to write a KCL at this node, basically starting from VR. So there are a bunch of currents that are going out. So I have this current, which I refer to it as I1. I have this current that I refer to it as I2. And I have this current that I'm referring to it as I3. This current here is 0, of course, practically speaking, because the input current to input port terminal of the op-amp is 0 because its input impedance is practically infinite. Okay, so I'm going to write KCL now. So KCL at negative or inverting input terminal of op-amp . Okay, so that means I am going to write I1 plus I2 plus I3 should be 0. The sum of the 3 outgoing currents should be 0 as shown here. Okay, so if I do that, then substituting for these currents, obviously I1 is VR minus 8.2 divided by R2. So that is simple. I'm going to just do that. And the same for the rest. So it will be VR minus 8.2 volt divided by that is resistor R2, I believe. So it will be R2. And then for I2 is the same story. It will be VR minus Vout divide by the RF. So VR minus Vout divide by RF. And then finally for R3, it will be just simply VR over 1K. Equal to 0. Okay, so if we clean up everything, what we're going to get out of this equation is a very simple one. We're going to get this equation that is basically Vout equal to RF over R2 plus RF over 1 kilo ohm. So RF over 1 kilo ohm plus 1 times VR minus 8.2 RF over R2 times 8.2 volt. Okay, this is an important equation. Now I'm going to name this coefficient as just K. So therefore, as a result, my equation becomes simply this one. It becomes Vout is equal to K times VR minus RF over R2, 8.2 volt. So let's name this equation 4. Okay, now, what is the meaning of this? We're going to substitute for VR from equation 3. So I'm going to substitute for VR using equation 3. And at the same time, I'm going to substitute for RT using equation 2. So I'm going to do that. Okay, so what's going to happen is this one. So equation 4, when substituting equation 2 for RT, and when substituting using equation 3 for the value of VR, we're going to get this outcome. We're going to get Vout equal to, okay, so let's keep K as it is. So it's going to be K R2 over R1, sorry, RT becomes R0 times, so let's keep the rest of it outside. So I'm going to keep 8.2 here, K 8.2, or let's say 8.2K. So 8.2K, and then we have R0 over R1. I'm substituting RT. R0, 1 plus alpha T minus beta T squared. And then we have, that is replacement for VR. And then we have VR is 1 plus delta T remaining minus RF over R2 times 8.2 volt. Okay, so what is the benefit of writing it this way? The benefit is we are now getting the result we wanted. So we can say Vout, so Vout is equal to 8.2K R0 over R1 and 1 plus alpha plus gamma T plus alpha gamma minus beta T squared minus beta gamma T cube. So we are getting to what we wanted, basically, minus RF over R2, 8.2 volt. Now, recall desired or target Vout is 1 over 50 temperature. So what is the meaning of this? This is equation 1 that we had. So the meaning is we want this to be 0. We want this to be 0. And we will set this one properly. So let's see. Okay, so step 1. Alpha, gamma minus beta should be 0. That means gamma so that we don't have the second order nonlinearity, because the desired equation doesn't have a second order nonlinearity, just first order. So gamma should be equal to beta over alpha. Great. Beta and alpha are beyond our control. They are just parameters of purely RTD. Okay, so if we compute them, we can compute the value of beta. So beta over alpha, we can compute it. It's basically, as I said, 5.78, 10 to the power minus 7, divided by 3.91, 10 to the power minus 3. So that can be computed. Nothing special about it. Okay, good. That's the value of gamma, which basically set this one to 0. Perfect. Okay, at the same time, this gamma is very small. If you compute this, we are talking about, so if you compute this gamma, we are talking about something on the order of 0.148, let's say, times 10 to the power minus 3. So as a result, because beta and gamma are very small, this one will be very small. So this means beta times gamma will be roughly 0, is very, very small. So approximately 0. And therefore, it will automatically take care of not needing to worry about the third order nonlinearity. So now the only question is, okay, so what's the outcome then? If we set everything like this, then V out becomes simply 8.2 K R0 over R1. Let me just clean it. Okay, so 8.2 K, and here there is this component here. So we have minus RF over R2, that's 1, and then the rest of it is simply 8.2K R0 over R1 times alpha plus gamma times T. Okay, so in this formula, this is our intercept. And this is our slope. So let me just clean it up. And this is our slope. Obviously, when you look at the desired slope is 1 over 50, and intercept is 0. So we're going to do that exactly. Intercept has to be 0, slope has to be 1 over 50. So how do we set these? If we adjust these values, what we're going to get is, we're going to get RF over R2 naturally is K R0 over R1. That's equation 5. And we're going to get here, obviously, K R0 R1 is RF over 2. So therefore, from this outcome, we're going to get 8.2 times, using equation 5, obviously, 8.2 times RF over R2 times alpha plus gamma equal to 1 over 50, the slope. The nice thing is only unknown. Sorry. This thing is only unknown. Obviously, alpha and gamma is known, so therefore it gives us the view that RF over R2 has to be roughly, let me just make sure I'm not missing something. Okay, has to be roughly 0.6 with the values we have in mind. So now we're gonna, let's name this equation 6. So I'm gonna use equation 6. And using the value of K, which is defined here. So I'm gonna use that as well. So we're gonna get basically 0.6, which is RF over R2, equal to K is RF over R2 0.6. So This is RF over R2, and this is RF over R2, and then plus RF over 1K plus 1 times R0 over R1. R0 is 100 ohm, and R1 is 10 kilo ohm by default. So it is 100 over 10,000. Okay, if we use these, then we find that RF is roughly on the order of, say, 57.8 kilo ohm range, or 58 kilo ohm, so roughly. And when we go back and use 7 and 6 together, so from these two guys together, we get R2 is roughly 97.3 kilo ohm. Okay, so with that said, the only remaining thing, given that we found almost all the resistors we had in mind, the only remaining thing that I need to compute is the value of Rp, which is almost there. So in the value of Rp, if I go back to here, we already computed gamma, which is, here. There you go. So if I use that, so basically if I use this one, and if I use the outcome here, then the only unknown basically is R1 Rp over 1 over 410 is equal to gamma, which is known or computed already, and the only unknown is Rp. So if we compute it, because R1 is just 10K, if we do that, then we get Rp is roughly equal to 165 kilo ohm. So in summary, what we found in this computation is RF is roughly, so I'm just gonna write rough numbers. So is roughly 58 kilo ohm, or let's say 57.8 kilo ohm, and R2 is approximately 97.3 kilo ohm, and Rp is approximately 165 kilo ohm. So with these values found, the circuit is now designed, and it can provide this sort of a weak positive feedback that gets rid of or compensate for the error resulted from having a dependency on the second order nonlinearity, and the output will be now a linear response, which was the thing we were looking for. I hope this example is helpful. Thanks for watching.